Astronomers have discovered a mysterious dark galaxy that emits no visible light. Apart from a small fraction of stars, more than 90% of it is composed of dark matter. At first, the researchers thought it was a regular dwarf galaxy with very few stars. However, a detailed analysis of the galaxy revealed it's an oddball that defies all expectations. Its properties challenge our understanding of extragalactic astronomy. Furthermore, this dark galaxy could solve one of the biggest astronomical mysteries, the missing satellite problem. But the intriguing question is that if it emits no visible light, then how did astronomers find it in the first place? How did they even conclude it's a galaxy millions of light years away? Finally, and most importantly, what's the missing satellite problem that has puzzled astronomers for decades? The missing satellite problem, also known as the dwarf galaxy problem, is one of the most important puzzles in extragalactic astronomy. It's a discrepancy between the observed dwarf galaxies and the number predicted by cosmological simulations and the LCDM model. Dwarf galaxies are tiny galaxies that contain up to 1 billion stars. They orbit bigger galaxies, such as the Milky Way, like natural satellites. The Large and Small Magellanic Clouds are two examples of the Milky Way's satellites. The dwarf galaxies are influenced by the gravitational potential of the host galaxies, but are stable astronomical entities in themselves. Many dwarf galaxies have been discovered over the years, bridging the gap between the observed and predicted number. A 2018 paper even claimed to have solved the missing satellite problem. However, this is only a partial solution because there is another problem. It's with detecting a peculiar class of dwarf galaxies called the ultra-faint dwarf galaxies, or UFDs. They only contain a few hundred to a few thousand stars, making them some of the faintest galaxies known in the universe. Their structures are mostly dominated by dark matter. Astronomers are interested in them because they contain valuable information about the early universe. All the UFDs discovered so far are very old galaxies that formed just a few 100 million years after the Big Bang. Now here comes the most exciting part. The reason why the missing satellite problem still exists could be dark galaxies, the primary focus of this study. A typical galaxy contains gas, dust, star clusters, a dark matter halo, and a supermassive black hole at the center. But dark galaxies, conversely, are objects that contain almost no visible stars and are dominated by dark matter alone. They are dark matter halos that have failed to ignite star formation so far. Their discovery could explain why ultra-faint galaxies are so scarce, providing a complete solution to the missing satellite problem. So far, they were hypothetical. But now, astronomers have found the first dark galaxy in nature. To understand this discovery, we just need to answer two questions. The first is that if dark galaxies do not emit visible light, how did astronomers discover it? Well, dark galaxies are predicted to contain detectable amounts of neutral hydrogen gas, specifically emitting the 21 centimeter line. It's a spectral line produced when an electron in a hydrogen atom flips to configure its spin anti-parallel to that of the proton. This spin flip produces a spectral line having a wavelength of 21 cm in the radio region of the EM spectrum. But not all hydrogen clouds or H1 clouds are dark galaxies. They could be tidal debris, material stripped off some galaxies or clusters due to tidal forces. So an ideal candidate for a dark galaxy must be isolated and far from other galaxies. Such isolated clouds of neutral hydrogen are called blind H1 clouds. They are not associated with any astronomical object. H1 surveys detect these clouds, and one of them was used by this research team. The discovery was made using the 500-meter aperture spherical radio telescope, or the FAST telescope. They found a candidate and named it according to its celestial coordinates. The distance to this H1 cloud is 28 megaparsecs, or 94 million light-years, corresponding to a redshift of 0.0083. Now, once we've found a potential candidate using radio waves, we need to answer the second question. How did astronomers conclude it was a galaxy? The answer is morphology, or simply the study of shape and structure of the H1 cloud. Astronomers found three critical clues that showed it's indeed a galaxy. The first is the distribution of neutral hydrogen gas in and around the cloud, as revealed by the study of column density maps. It indicated that the structure of the cloud was very compact. The second clue was the double peak in the global H1, or the atomic hydrogen profile. It's a plot of the measure of the intensity of the 21-centimeter emission line, or the flux of neutral hydrogen, as a function of the velocity of the motions of the gas along the line of sight. If there's a double peak in this graph, it means there's a disk-like structure. Why? That's because it indicates the gas clouds are rotating around the galaxy's center. So the two peaks correspond to the approaching and receding sides of the disk. The final clue came from the position velocity diagram of the H1 cloud. It showed an S structure. The position velocity diagram tracks each position according to its velocity. The two ends of the S shape represent the ends of the spiral arm of a disk galaxy, and the central dark regions correspond to the double peaks in the global H1 profile, or the regions of the disk. So these 3 points enabled the astronomers to conclude that it's indeed a disk galaxy and not just an H1 cloud. But the very definition of an ideal dark galaxy requires it to be isolated. So the last thing astronomers needed to confirm was that it's a lonely galaxy. For that, they studied the images of the galaxy and its surroundings in different wavelength bands. They included optical, near-infrared, near-ultraviolet, and mid-infrared regions of the electromagnetic spectrum. Consider this figure from the research paper. The inner red circle represents the expected disk diameter of the dark galaxy. The dashed circle is 3 times that diameter. Of course, the galaxy can't be seen here because it can only be observed in radio wavelengths. The yellow and black disks are optical stars identified from the Gaia mission. Since Gaia only probes the stars and other objects in the Milky Way, it's clear that these stars in the image are within our galaxy, in our line of sight. Therefore, they are not a part of the dark galaxy. Also, using parallax, the distance to the farthest star was found to be around 13 kiloparsecs, well within the range of our galaxy. The figure clearly shows there's no optical counterpart of the dark galaxy. Then, the near-infrared and near-ultraviolet images displayed no signs of any star formation or galactic neighbor that could be visible in these 2 bands. And lastly, the radio emissions from this galaxy only correspond to the 21-centimeter line, or neutral hydrogen. This confirmed that it was a lonely dark galaxy, the first ever found. The astronomers compared it with other galaxies, having a close resemblance to it. They first applied the baryonic Tully-Fisher, or the BTF relation. It's a graph between the baryonic mass of the galaxy to its rotation velocity. The resulting graph showed that the newly discovered galaxy is a typical disk galaxy, but another graph showed it's an oddball. When they analyzed the relation between the H1 mass-to-light ratio and the B-band magnitude, they found it stands out compared to low-surface brightness galaxies in black and almost dark galaxies in green. They concluded it's one of the darkest gas-rich galaxies ever discovered. The dark galaxy discovered by FAST has a baryonic mass of 100 million solar masses and a dynamic mass of 5.1 billion solar masses. Baryonic mass corresponds to stars and gas inside the galaxy. The ratio of these two numbers indicates there's plenty of dark matter inside this galaxy. Furthermore, its properties suggest it could be in the early stages of galaxy formation as it lacks any stars. Hence, we may have actually found a baby galaxy still in its cradle. Discovering such dark galaxies will enable us to understand galactic evolution better. And finally, it may help us answer why ultra-faint dwarf galaxies are so rare. Recently, amateur astronomers discovered a mysterious structure close to the Andromeda Galaxy using backyard telescopes. This gigantic structure has stumped astronomers as they struggle to explain its origin. You can watch this episode of the series to learn more about it.